Hi everyone, welcome to Lab 4, Faraday's Law. So the purpose of this lab was to study the interaction between a falling magnet and a tube of aluminum foil. The materials included glow script, a bar magnet, and aluminum foil. And the results overview was that the experimental time was 0.968 seconds and the computational time was 0.861 seconds. So the system was the bar magnet and aluminum foil, and the surroundings are everything else. So the fundamental physics ideas were, first of all, we have Faraday's law, saying that a changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux, with the induced voltage opposing the change in flux. And that part is Lenz's law, and the formula is below. And then next we have the Biot-Savart law, and that states that a steady current produces a magnetic field around it with the strength depending on the current and distance from the current carrying segment. The formula is below for that as well. And then next we have Newton's second and third laws, stating that the net external force equals the change in momentum over time, and that for every action there is an equal and opposite reaction force. So the measurements above are the initial conditions for this experiment. We have the tube dimensions, the magnet properties that I already found in a previous lab, and then the average time was after I performed 5 trials, timing the time the magnet was inside the tube, and that was 0.968 seconds on average. Okay, now for the code, the initial conditions. So the physical constants and the properties of the magnet are all written there on the left, as well as the geometry of the tube, and that was measured and shown on the previous slide. And then next we calculated the magnetic field of the bar magnet, and that's the formula written out beside that. And then calculated the magnetic flux, and that's the formula there as well. Okay, now to code the forces, I first calculated the magnetic force on the magnet, and that's shown on the left. And then on the top right, I calculated the gravitational force on the magnet, and then I added those two together to find the net force on the magnet, and then updated the magnet's velocity and position. And then here's the visualization or the output of the code. The graph on the left shows that as the magnet enters and leaves the tube, the gravitational force is greater than the opposing magnetic force. However, as soon as the magnet enters the tube, it travels at a constant velocity because the gravitational force equals the magnetic force. Now to interpret the solution, so the red is the counterclockwise current and the blue is the clockwise current. What happens if you flip the magnet? The magnet would fall the same as before, but the current directions would be switched. How does the total time in tube of the real-world system compare to that of the computational system? The computational system produced a shorter time in tube because it didn't take into account air resistance, and also human error was a factor. What does the plot shape say about forces acting on the magnet? Gravitational force is greater than magnetic force when entering and exiting the tube, but it is equal within the tube. There were several sources of error: friction, when the magnet hit the sides of the tube, slowing it down, and air resistance, which was not taken into account for this experiment, as well as several assumptions like negligible air resistance, the bar magnet acting as a magnetic dipole, and the only forces considered on the system were magnetic and gravitational. Now for the discussion. So what is the resistivity of the conductor? Were reduced as close as possible to zero, how would the dynamics of the falling magnet change? From Ohm's law, decreasing the resistance would increase the induced current, producing a stronger opposing magnetic field and slowing the magnet even more. And also, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be less current rings within the tube, which would produce a weaker opposing magnetic field, causing the magnet to fall faster. And that's it. Thanks for watching.